Today we are going to see a second part, or the complete solution to this problem that we have on the screen, and that is the building controls with operational amplifiers, or maybe I should label it the basics of controls using operational amplifiers. In other words, the circuits that we are seeing right now and these operational amplifiers are used to design the actual hardware that goes into building different types of control. So using this little example, we're gonna see how that comes out. So let's get going. I'm gonna continue from the last video that we did, the last lecture, and you see, here's the example. You have the circuit in here that has a capacitor and a resistor on this side, and it has a voltage input, obviously, and then you have this operational amplifier with this RC circuit connected this way. Okay, so the question that we have is, can we relate this voltage output to the input voltage? That's the question. And if we do, how are we going to do that relation? So we need to reduce this whole entire circuit to some factor that relates the output voltage to the input voltage, and obviously that relation is so-called a transfer function. What we saw in the last lecture and previous video is that this section of the circuit can be reduced to its impedance, like here, see. And these two elements in here, they can also be reduced to their impedance here, some equivalent, as if they would be just two resistors. Okay, so what I did, or what we're doing right now, is achieving the reduction here and achieving the reduction here. What we saw on the last time was the reduction on this side, which is right here, see? So using of the concept of parallel connections for the solution of two resistors connected in parallel to find out the equivalent, in this case not resistance but impedance, it has this form, like 1 over R equivalent is 1 over R1 plus 1 over R2. So having done this, using this idea, we can put the impedance of the C element over here, the impedance of the R element over here, and treat the Z1, the equivalent impedance, as if this would be resistor, see? And that's exactly what I'm doing over here, see? So we have 1 over Z1, which would be the total resistance, is this 1 over CS, and the other one 1 over R1. So we have this expression in here. So if we invert it, or you say the 1 over Z1 is going to be CS plus 1 over R1. So we need to do the same thing for the other part right here. And that's, so here's where we stopped. And so now we are going to continue to do the other part. Yeah? So let's look at writing what the impedances are for the other part of the circuit. I think this one right here, this one. Just to make life a little easier, I think I'm going to draw it down here. You would say for the, let's call it for the branch on top. I think is what we're going to say. So let's just put like a title. It says for the so for the top branch. So in here we let's just draw the circuit to make sure that we know exactly what we're talking about. We are talking about this one right here. See right here. This one right there. So let's just draw it over here, and that is going to be like this, where you have R sub 2 over here, and then you have C sub 2 here, like this. You see, this is the normal form. If we write in the impedance form, we can say that this one here is like R sub 2, but this one is 1 over C sub 2 times S, and this of course is equal to this Z2. So let's just put like in parentheses here. So this would be the impedance form. This one we could call it equivalent impedance. Form. Yeah. So you have the equivalent impedance form right there. And so we can say, if we write in the equations, that Z sub 2 is going to be R sub 2 plus 1 over C sub 2 times S. So what we have in here is that we need to relate we are at this point right here, see, right here, like this. And we already saw that from the prior examples, remember the inverting operational amplifier, we already saw the result of that. And maybe I'll go back just to make sure that we are on the same page. The inverting operational amplifier, remember in here, when you have exactly like what we have right now, you see here, what was the result for the output voltage? It was the relation between the two impedances with a minus sign. That was what it did. This is called an inverting operational amplifier. So this circuit that we have in here, in front of here, this is exactly what we have in here right now. You see it here? No, here, right here, like that. This is exactly what it is. So if that is true, well, let me just put here B out and then B in, so that do you see it now? This is the inverting operational amplifier. So basically what we have is that the relationship between B out over V in was minus Z2 over Z1. You could say, using the derivation of the inverted, the what we call an inverting operational amplifier. Inverting operational amplifier. Very good. So if this is the case, what do we have? We say, okay, V sub 0, V output over V in is minus, and then what is going to be Z sub 2? Z sub 2 is going to be R sub 2 plus 1 over C sub 2 times S, and Z sub 1, from what we learned on that inverting operational amplifiers, is 1 over C sub 1 times S plus 1 over R1. Okay, so using this, we can reduce this and do a little bit more of a, how can I say, just a reduction of these factors to come up with an expression that you have in terms of the, do a little algebra on both sides here, and you will have this perhaps I think would be a good idea to do one more step, because you can see it in here. This is basically, this is going to go up, is like the minus multiplied by C sub 1 times S plus 1 over R1, and then you have it like this, see, R sub 2 plus 1 over C sub 2 times S. Because we want an expression with a numerator and a denominator, we multiply these two. So let's just give it a try. Here you have, this is a minus, and then you will have like a C sub 1 times R sub 2 times S plus C sub 1 times S divided by C sub 2 times S. That's right there, this cancel. And then you have plus R2 over R1, and then plus 1 over R1 C sub 2 times S. See? And so we keep on working on this. If we try to get us an expression of the numerator or on the denominator, you could say that the denominator is R1 C sub 2 times S, and then you multiply this by the numerator, which would be minus R1 C sub 2 times S times C sub 1 R sub 2 times S, and this would be plus R sub 2 times C sub 2, R sub 2 times C sub 2 times S plus 1. I think I have a, this minus sign outside makes this a plus, so so that we don't make a mistake. The fact is that you have this transfer function minus sign, and then you have this in here. You have R1, R sub 2, C sub 2, C sub 1 is square. So you see this is a factor right here. Plus you have the other factor, and I think I'm missing a term. So yeah, this R2 over R1 and S, so we have an end here, and then plus 1. There's something I am yeah, am I right? Okay, let's review this so that I don't make a mistake. So if you multiply this by this, you get this factor. If you multiply this by this, you get this. If you multiply this, you get this. If you multiply this, you get that. I think we're fine, right? Yeah.
Your C1 over C2 factor, so it would be C1 over C1.
So this divided by this produces this, so that's not a problem. This one here divided by C sub 2 is, yeah, we need 4 terms and we are missing 1, right? So we have one more in here, that this divided by this is R1 times this times C sub 1, right? C sub 1, R sub 1 times, now we are fine. And so having done this, then we have C sub 1 times R1 plus C sub 2 R sub 2, and then you see this factor is S, and then plus 1. You see now it has taken the shape of the numerator and the denominator as we would like. And then what I am trying to say to you is that if you put numbers now into this, if you plug in the numbers that you're giving, you are going to end up with a polynomial that has the value on something like, let's see, we have minus, I think is 1.232 s squared plus, you will have something that says 45.9 s, and then plus 22.5. okay, this thing here is called the, remember it's in the S domain, is this is called the derivative control, derivative term. This is called the proportional control. Excuse me, I think in here we have, I'm missing something. This is the proportional control. And this is called the integral term. This is why it's called PID controller, and it stands for proportional and then integral and derivative control. So I just wanted to show you how when you put the numbers, you have basically come up with you have built this PID controller with this circuit right here. That was the objective of this exercise. Yeah. So we can see here the whole process. You go from the circuit, then you convert it into the equivalent impedances, and using the concept of parallel connections in here, you have this one, and then you reduce it to impedance Z sub 1, and then to reduce the other branch over here, this one, we did it over here, and we reduce it to Z2. Then using the derivation, the previous derivation for an inverting operational amplifier, we knew that the output in relationship to the input was minus Z sub 2 over Z sub 1. And right here, if you put this into the computer program using the symbolic toolbox, we should be able to come up with this transfer function. So, which turns out to be that this, if you build this circuit, you'll end up with this PID controller. See? And that's the whole idea behind doing this operational amplifiers examples, because they are the basics of building controls.